All right, physics reaction video number 51. I did a search for, I think it was honors physics from this week, and I found this. So here we go.
Hello, honors physics students. Let's start with problem number 5 in your projectile motion practice problems. I know it seems a little bit strange why we're now just starting with number 2. That's the one we left off with. But this one is a full and complete problem, so I think it's going to go through all the aspects of a horizontally launched projectile that we need to do. So go ahead and read letter A, and like it says to right there in the space provided, go ahead and sketch out a picture of what's happening.
So already I really love the scaffolding, right? Like, so first of all, it's explaining why doing this one, but you know, what a great reason, right? So it's a problem that has all of the features, and let's see it all in one place. And then also just, you know, literally modeling how to read it. Okay, let's read letter A. It says do this, so let's do it. And then also notice the framing and the scaffolding already provided. Like, look, you're going to have to do some vertical work. You're going to have to do some horizontal work. Let's just keep it straight. So very cool.
Okay, your picture doesn't have to look exactly like mine, but I drew something like this, right? Using the drawing tools, some sort of level ground. We got a cliff going on there, and there's a picture of a cannon shooting out a cannonball. Mine's going to be shot out to the right. However, if you have yours shot out to the left, that's absolutely fine. You don't have to change anything about what you've done. Just everything's going to be sort of flipped in the sort of the direction. That's absolutely fine.
So I really liked that pause that he did before he showed his picture. You know, these pregnant pauses in classes, you know, instructors are told to count to 10, these sorts of things. By the way, that count to 10, it works. I mean, it really does. And the lesson I learned from some really smart people that I've interacted with is that if you do the count to 10, don't count out loud. Because it turns out that if you count out loud, that's all people are focusing on is sort of your lips and the counting. And so I just stand there, and I do it in meetings all the time, in these virtual meetings. I just sit there and mentally count to 10, and humans can't stand it. And so they're going to do something. And so what he's saying is, or what he's thinking, and what I think he's accomplishing is the students are, all right, fine, I'll start drawing something. And you know, then he lays in this nice drawing with beautiful horizontal lines, a funny looking cliff, and of course a really nice cannon. But I loved what he said. He's like, hey, don't freak out, don't change yours. Yours is probably fine too. You know, there's really only a couple of things that need to be in here. There needs to be a height. I'm guessing it needs to be horizontal. And this needs, I guess, this line here also has to be horizontal. So, you know, not a whole lot that has to be in there, but it needs to be nice and big so you can label some stuff. So I really thought that was great.
It does say label the given information, and it says it's being launched at 70.7 meters per second, purely horizontally. Okay, so we're going to label like
70.7. 70.7. Isn't that 1 over the square root of 2 times 100? Let me check. I think it is. I'll turn my calculator sideways to be able to do square roots. So 1 divided by the square root of 2. Yeah, times 100. So let's watch for that. Could it possibly be that the square root of 2 is going to be useful in here? Let's see. So if you did 1/2 mv squared, for example, of the initial energy, you're going to get a nice, well, I guess we don't know what the mass is yet, but if you square 70.7, what do you get? 20,000? No. Let's see, 70.7 squared. I could use my calculator. Is, oh, okay, it's almost exactly 5,000, right? So are we going for round numbers, or is this just some made-up number? Interesting.
so. Now notice I'm calling it V sub L. L in this case stands for launch. You might have called it V naught because it is certainly the initial speed that's being launched at, but that's going to get a little bit confusing as we start to set up our chart because we're going to have V naught on the vertical side. We will also have V naught on the horizontal side, and I don't want to confuse the issue. So we're going to call it V sub L for the launch velocity.
Cool.
We know that the cannon is 34 meters off the ground, so I'll label that on the picture as well.
So this is really interesting, right? So exactly where this arrow measures to. So if he had only measured to the actual cliff here, he'd be off by, half a meter or something. And he didn't actually have this arrow go all the way up to the ball. So there's some subtleties there, right? There's no question that everybody knows you're going to plug 34 meters into this stuff here, right, onto the vertical side. But getting the drawing right, I think, is important. So I do wonder, if it's sort of interesting. It's definitely not at the level of the cliff, but it also doesn't quite get up to the ball. So just a subtle little thing. And I ask you guys, when you do that kind of thing, when you're prepping, you put this wonderful thing together and you put it on there and you're proud of it, and a student asks a question like that's a curveball, right? Like, you can stop and apologize. You can, let me fix it. Or you can say, okay, hey, I'm really glad you pointed that out. Let's just keep in mind that that's what we mean, that kind of stuff. So, for sure the 34 meters is going to be down here. I do wonder if he's going to comment at all, whether there's a tiny little hitch here. So just the types of things that catch my eye.
And then it says to draw the path of the cannonball. So if you haven't done that yet, go ahead and do it.
Ooh.
And remember, it's not just any sort of curved trajectory. It's going to be a parabolic trajectory. It's not like the cannonball goes straight for a while and then falls. That's only what happens in cartoons, right? When the character all of a sudden realizes there's nothing underneath them. No. In reality, the cannonball starts to fall as soon as it leaves the cannon, and so it's going to follow some sort of path like this. So there's its parabolic trajectory. Okay, so at this point, if you have some...
So I'm just looking at this, wondering how this came to be, right? So is this a graphic, one of those graphics where you put in an anchor point, a control point, and then another anchor point? This is quite flat. I would say this is not quite a parabola. So it's a really interesting question, right? So how hard do you work at using drawing tools that can get this perfect? This doesn't look exactly like a parabola to me. I would say it should be curving more. Here, maybe it's more like a hyperbola. So big question, who cares, right? What he said before is really the important piece. The drawing, I think, is really just going to be there to help us. I have a little spinning blue circle. The drawing is really only there to help us sort of label things later. So from that perspective, perfectly fine. And honestly, not trying to get it absolutely perfect helps the students know, okay, this is just a little dashed line to help with labeling things. I'm just going to back up a little bit.
Parabolic trajectory. Okay, so at this point, if you have some experience doing projectile problems, if you want to go ahead and start setting up the chart and solving the problem, that's fine. But more than likely, this being only the second time we're doing this as a class, maybe you want to follow along with me doing it here and then pause the video when I tell you to. So we have our vertical versus horizontal chart set up, and one of the first things we want to do is establish positive directions, just like we had done when we did it in the notes on the grid in class.
Nice.
All right, so the cannonball is clearly falling down, so we're going to call down the positive. I think that makes the most sense.
Okay.
And it's being shot to the right, so I'm going to call right positive. Obviously, if you have the cannonball going to the left, you're going to call left positive, and that's absolutely fine. Nothing's going to change about your solution. But we have two different dimensions of motion. We should have two different positive directions.
That's really cool.
And then we're going to start to label all the information we know, specifically the initial velocities and the acceleration. So if you want to pause the video here, and on the vertical side and the horizontal side, list what V0 is equal to, and list what the acceleration is.
Cool. I really loved, by the way,
this is a purely
positive
horizontal launch, which means when it's coming out of the cannon, it's not going up or down. So the initial vertical velocity is going to be 0. For the horizontal, well, that's what the 70.7 meters per second is. So I write V0 equals 70.7.
So this double usage of V naught, right? So some people are going to put a Y here and an X here, like a double subscript. But this nice, beautiful line here is really trying to keep these separate. I don't know. I see lots of value to the way he's doing this, so that you basically treat these two as two different physics problems using the same structure for both. But what danger is there that the student's going to look up and grab the wrong number when they plug into if they have to plug into a calculator?
Let's talk about the accelerations. Remember, the whole idea is that a projectile problem is really just an object in free fall. As soon as the cannonball leaves the cannon, it's already in free fall, and so the vertical acceleration we know is going to be 9.8 meters per second squared, the acceleration due to gravity. But is it positive or negative? Well, let's remind ourselves, of course, it's accelerating down, and we call down the positive direction.
Man, that's great.
If we agree, of course, it's going to be a positive 9.8 meters per second squared.
That's really great.
What about on the horizontal side? Well, now we bring the forces into play. Once the cannonball leaves the cannon, the only force acting on it is gravity, and that's a vertical force. And since there's no other forces, there's no other sort of acceleration, right? And so with no horizontal forces, there's no horizontal acceleration. This is going to happen every single time we do a projectile problem. The horizontal acceleration will be 0 because there's no horizontal forces. Now, before we move on, let's remind ourselves what this means. If the horizontal acceleration is 0, that means the horizontal velocity never changes. And
Love
so
it.
if it's launched at 70.7 meters per second, at any other time later in the problem, the velocity will still be 70.7 meters per second in the horizontal direction. That also means if we were to take the average velocity, well, the average of 70.7 and 70.7 is 70.7, and so we can write this also equal to v bar. This is going to happen every single time for a projectile problem. So it's a good idea to do it right from the start to remind yourself that no matter where you are in the problem, no matter when you are in the problem, the horizontal velocity will be 70.7 meters per second. And this takes the guesswork out. If just in case later on in the problem we need to know what the horizontal velocity is, we've already written it for ourselves. The last remaining piece of information is this 34 meters. Obviously, it's going to be a vertical displacement. It's falling straight down 34 meters. Although even though it's not moving straight down, that's the vertical displacement of 34 meters. So we're going to write delta y equals 34.0 meters. You can call it delta x if you'd like to, but if it's going vertically, I like to call that delta y to remind myself that's in the vertical direction.
Nice.
Notice I left the sign off of this. All right, so let's think about this. Should this 34 meters be positive or negative? So go ahead and put the sign on it if you haven't already. It should be kind of obvious, I hope, right? It's clearly going down, and we call it down the positive direction, so that's going to be a positive 34 meters.
It's really interesting when you have a measurement, something you can take a tape measure to, right? Usually that's just a positive number, right? So the height is 34 meters, but he's going here for sort of y final minus y initial. And so he's calling y final, well, let's assume he puts a 0 here, right? If y initial is 0 and y final is 34, then because of his choice here, it's 34 minus 0. If he calls this 0, this is actually negative 34. And 0 minus a negative 34 is so. I mean, this is interesting. I think that at some point you might just want to say, okay, time to be able to do the right hand side. Well, I actually don't know what questions are being asked here. My guess is how far does it go? Usually it's how far does it go and how fast is it going. So we're going to need time in here somewhere. And so really you just say, okay, if this is happening to you, how long does it take to go this far? And of course, if you put a negative number there, that wouldn't make any sense. So I really love the consistency that he has here, but I'm struck when there's physical measurements, literally something you walk up with a tape measure to measure, that I just don't think of people ever putting negative signs in front of that. And so I would call that the height. But I guess if you're calling it delta y, it's technically y final minus y initial, then yeah, it does have a sign.
Okay, so now it's time for us to actually start solving the problem. So letter B asks, how long does the cannonball take to land? Again, if you have some experience doing this, you want to try to pause the video and try it on your own, that's great. If you want to follow along with me, also good. So our goal is to play around with some kinematics equations with the given information, working on one side or the other, and try to find how much time it's going to take to land. I will give you a little bit of hints in case you're not quite sure what to do. Maybe you want to start on the vertical side.
Love it.
Okay, so we know the initial velocity, we have the acceleration, and we have the displacement vertically. All we use the
I just want to pause for a second because I'm curious about any of you who actually use these sort of built-in quizzes in your learning management system, because there's definitely sort of a market out there for people to not only encourage their students to pause the video, but like to force them to have to do something before they're even allowed to watch the rest of the video. He's not doing that, right? He's like, look, you guys, come on, this is the only way you're going to learn is if you have a pencil and paper handy while you're watching these things. Because we know that when students just watch the videos, or it's very similar to when students read solutions, this is what they do. Oh, yeah, yeah, oh, of course, yeah, oh, yeah, of course. And then when they do a problem without that aid, they get stuck quite early and don't realize that when they were saying, yeah, of course, when they were looking at the solutions maybe you provided or they found somewhere, there was a choice to be made, and yes, that choice seems right. But if you're not confronted with the other choices, you don't realize how hard that might actually be. So anyways, he's asking them to pause and to say, oh, what are we going to have to do? He gave the hint that time is probably going to be over on this side. And, I really love to talk with them and find out, how often do your students literally do that? Because unfortunately, I guess the cynical part of me says that the students just keep on trucking. They just keep, maybe they even fast forward because they just want to see it. And that want, right? They just want to see it. Where does it come from? Well, is it that they don't know how to do it? Is it they don't feel like doing it? Is it they know that it's going to come anyways, right? So that I think is tough to navigate. I think this market of video sites that sort of enforce a quiz that are interesting, but I can imagine that drives students crazy too, especially the students who are like, yeah, I get this. Come on, I just want to see the part I'm confused about. So anyways, I find that all really, really, really interesting. So let's see how much longer. I'm going to just back them up and then curious how long this pause is.
We know the initial velocity, we have the acceleration, and we have the displacement vertically. All we use the time. So we can do this in multiple steps, and there's nothing wrong with doing multiple steps, but it will be a little bit easier, a little bit more efficient if we use the displacement equation, delta y equals v naught t plus half at squared. Now, if you already paused the video and solved it and you didn't use this equation, that's absolutely fine. There are other ways to do it. I'm just going to show you one way of doing it. As long as you get the same answer, it really doesn't matter. Now, this is one of the most important parts about projectile motion, which is really two-dimensional kinematics. That this dividing line right down the middle of the vertical and horizontal chart separates the information in either of the dimensions. And so if you're on the vertical side, you can only use vertical stuff, right? Well, on the vertical side, we look up here, we say, oh, we know what v naught is 0, and anything times 0 is 0, so we can cross that off. But we can't use any of the horizontal stuff on the vertical side. It doesn't work that way. Okay, so what we want to do is, we see we have delta y, we have acceleration, we want to solve this for time, so as always, we rearrange algebraically. And of course, when we rearrange algebraically, we get our usual shortcut equation, t equals the square root of 2 delta y over a, and in fact, if you jumped right to that, recognizing you're allowed to use it, that's absolutely fine. Now, how do we know we're allowed to use this shortcut? Well, we can only use this shortcut when initial velocity is 0, because that's how the algebra works out. And on the vertical side, initial velocity is 0. Could we use this shortcut equation on the horizontal side? No, the horizontal velocity initially is not 0. This equation has no meaning. Okay, so at this point, go ahead and pause the video, put the numbers in, and find the time it takes for the cannonball to land.
So 16 divided by 10 is 6. Square root of 6 is...
Okay, so put your numbers in, and you should get 2.63 seconds. It's obviously a 3 sig fig problem, so you have 3 sig figs in your answer. Now, I did box this in, but let's just consider this for a second, right? We're only on the vertical side. This basically says if you take an object, this cannonball, and drop it from rest to fall straight down 34 meters, it should take 2.63 seconds. That means the cannonball, if it were to just be dropped, not launched horizontally, should take 2.63 seconds to fall straight down to the ground. But that's not what it's doing. It's actually falling.
So let's check that. So that's about 3 stories, right? 10 meters per story? Yeah. 3 stories high. So I'm 2 stories high. I drop something out of the window. 1001, 1002, 1000. Yeah. Yeah, that feels right to me.
On this parabolic trajectory. So is this 2.63 seconds really our answer? It seems like it's only the vertical time. We want the whole time. So what do we do? Well, hopefully you recall the video that we watched in class. That was a very similar situation to this, where we had one ball that was launched horizontally to the side and one ball that fell straight down.
Awesome. I was just thinking of that.
Together, we saw they fell the same vertical distance in the same amount of time. They hit the ground at the same time. And so it's a
great demo, great video.
Motion idea that the time to fall straight down is also the time to follow the parabolic trajectory, because the horizontal motion does not affect the vertical motion. And so yes, this 2.63 seconds is the time for it to hit the ground, even though it follows this parabolic trajectory, not falling straight down. All right, also letter C, we want to find the cannonball's range. Okay, so range, that's a new vocabulary term. If you don't remember what that is, go back to the notes page and look it up.
So the range could be one of 2 things. It's either this horizontal distance or it's this distance, which I find fascinating. Like how far away did the cannonball get? How far did the cannonball travel? Well, that's actually the length of this curved line, right? So there's 3 ways to ask it. How far did it get horizontally? How far away did it get? And how much distance did it travel? I'm guessing by this he means this distance here. Let's see. Let's back him up a little bit.
If you don't remember what that is, go back to the notes page and look it up. Of course, this is horizontal displacement. So obviously we're going to be on the horizontal side. So
the easy one.
Take your favorite kinematics equation and go ahead and solve for its range.
All right, so I'm just going to stop there. I think this was some really, really great stuff. I think my favorite part was this, right? Just really driving this home. I also loved how he, really talked about the separating line here. And he, for example, talks about how, well, hang on a second, is this a number that we can use over here? And he asked them to think back to some work that they had done before, like, yeah, this actually is a number that you can use over here. So that's really, really interesting. I guess I didn't watch long enough to find out if this ended up mattering, but it's interesting how just certain numbers catch my ear, catch my eye. All right. Well, I think that these sorts of problems are really, really tough. They have some subtleties to them. I think the splitting it up this way is really, really great. All right, everybody. Well, have a great day, and remember, physics teachers are awesome.